Chapter 9 is a discussion on solutions, and a reminder to you that all solutions are homogeneous mixtures. And what does that mean? Well, in Unit 1 we discussed that homogeneous mixtures are described by having variable composition. You can easily change the composition of a homogeneous mixture by adding more of one substance or another. So homogeneous mixtures have variable composition and they have uniform distribution, which means that a dissolving process had to occur. All solutions contain one or more solute particles or substances that are dissolved in a solvent, which is a dispersing medium. So the solute, one or more solute substances present in smaller amount, and the solvent that disperses the solute is present in greater amount. In a Chem 2A class, most often the solvent that we're working with in a solution is water. Note that a solvent doesn't have to be water, but water is a very common solvent, a very important biochemical solvent. And unless stated otherwise, the solvent that we're looking at in the solutions we're talking about is water. Solubility refers to the maximum amount of solute that can dissolve in a given amount or quantity of solvent. Usually that's specified as 100 grams of solvent. So saying this mathematically, solubility equals grams of solute that dissolve in 100 grams of solvent. Notice that solubility is temperature dependent. Solubility can change for most solutes if the temperature changes. So you would need to state the temperature associated with a given solubility amount. Solutions can be described as either unsaturated, saturated, or supersaturated. And just a comment that supersaturated solutions are not stable. Therefore, they have a very narrow, limited scope of focus. We'll discuss them in lab, but our attention will be spent describing unsaturated versus saturated solutions. An unsaturated solution, and notice I'm abbreviating solution SOL''N. Unsaturated solutions contain less than the maximum amount of dissolved solute. So notice when we describe solubility, we're talking about the maximum amount. If a solution is unsaturated, it contains less than that maximum amount of dissolved solute. So what that means is that, for example, if you're looking at a solid solute and you add more of the solid solute to an unsaturated solution and you stir, what will you observe? What will your eye see? You will see the added solute dissolving in a liquid solvent, for instance, such as water. So unsaturated solutions, you can add more solute and observe dissolving taking place. If the solution is a saturated solution, it contains the maximum amount of dissolved solute per given amount of solvent. What that means is that no more solute can dissolve in that solution. So if you added more solid solute, for example, if that's what you were looking at, a solid solute, if you added it and stirred, the extra solute would just settle and remain undissolved within the solution. Let's illustrate that with this substance, glucose, a very important sugar that is present in the body, commonly referred to as blood sugar. If you have glucose and you add it to water, glucose is a solid substance, add it to water, so put it in water, the solvent, glucose will readily dissolve, forming a glucose solution, hence the aqueous for dissolved in water. But you and I both know there's a limit to how much glucose you can continue to add to a given amount of water and have it dissolve. If you just kept adding more and more glucose solid to the solution, a point would be reached where you would see dissolved glucose molecules recrystallizing and forming the undissolved glucose solid. At that point, what's happening, arrows in both directions, we've seen that before when we looked at equilibrium. What's happening in this system is that you've achieved an equilibrium where the rate of dissolving of glucose is equal to the rate of recrystallizing of dissolved glucose back into undissolved solid. So arrows in both direction. Rate of dissolving equals rate of recrystallizing, and therefore no net change in the amount of dissolved glucose. You have formed a saturated solution. And solubility refers to the amount of a solute that can dissolve or has dissolved when saturation has been reached. A saturated solution will always be observed to have solution present and in contact with undissolved solute. So that's how you visually tell you've reached saturation. You've allowed time to pass, you've stirred, you have allowed dissolving to take place, but you've reached this equilibrium point, and you will always have undissolved solute in contact with the solution. Let's turn our attention now to factors that affect solubility. In other words, what factors affect how much solute can dissolve in a given amount of solvent? And I'm listing the most important factor with an asterisk. A, the chemical structure and polarity of the solute and the solvent. That is the most important factor in affecting or determining how much solute can dissolve in a given quantity of solvent. So why is chemical structure so important? Because the bonding arrangement of substances determine whether or not the substance is a polar or non-polar substance. And polarity determines types of intermolecular forces of attraction. In order to make a solution, you have to take the pure solute substance and separate its molecules or particles, to separate them from each other, which means that you have to break intermolecular forces of attraction within the solute. Likewise, in order for a solution to form, you have to take the solvent molecules and separate them from each other and break apart their intermolecular forces of attraction. Then you have to take your solute and mix it into your solvent and form new intermolecular forces of attraction between the solute and the solvent. Well, if all those intermolecular forces of attraction are similar in nature, then forming a solution will be very similar to, in fact, being in the separate pure state. So solute and solvent can readily mix together and interact with each other if their intermolecular forces of attraction are similar to each other. Therefore, we have this general description known as like dissolves like. But you would need to be able to explain that in greater detail if this were a quiz or exam question. What does like dissolve like mean? It means that polar solutes dissolve best in polar solvents. Why? Because both the solute and the solvent would share similar intermolecular forces of attraction. We know that dipole-dipole IFAs and hydrogen bonding IFAs are the primary intermolecular forces of attraction operating in polar substances. So polar solutes dissolve best in polar solvents. Likewise, nonpolar solutes dissolve best in nonpolar solvents. Why? Well, if both the solute and the solvent are nonpolar, then they both would share similar dispersion intermolecular forces of attraction. and can interact with each other in a very similar way as they would interact with molecules of their identical same substance. Let's illustrate that with an example. If you were considering methanol as a solute, and I'm giving you the chemical structure of methanol, its formula is CH3OH, but you would need to be able to think about that formula and draw the bonding structure. As soon as you look at the structure for methanol, you should recognize that there is a polarized hydrogen present in methanol, a strongly partially positive hydrogen because it's chemically bonded to an electronegative oxygen, nitrogen, or fluorine. So within the pure substance methanol, the strongest intermolecular force of attraction would be hydrogen bonding. Hydrogen bonding, the strongest intermolecular force of attraction operating and holding methanol molecules together. Well, if you wanted to dissolve methanol and make a solution, what should you choose as your solvent? Pentane, C5H12, or water, H2O. Now, looking at the chemical structure of pentane, C5H12, it's an organic compound, and we will introduce organic chemistry at the end of this semester. But here's what should be readily apparent to you, even though you're not quite sure of exactly how to draw the Lewis dot structure for pentane. As soon as you look at the formula and see that it contains only carbon atoms and hydrogen atoms, then you are looking at a molecule that you would classify as nonpolar. We know that a carbon-hydrogen bond is not a particularly polar bond, nor are the carbon-carbon bonds that are also present in pentane. So hydrocarbons we would classify as nonpolar molecules. Therefore, the primary intermolecular force of attraction operating between pentane molecules is dispersion IFAs. I don't think we need to spend much time talking about either the Lewis dot structure for water or its primary intermolecular force of attraction. We discussed that in great detail, and we know that the primary intermolecular force of attraction operating between water molecules is hydrogen bonding. Once we've identified that, we are in a position, using the principle of like dissolves like, to choose the best solvent to dissolve methanol from these two choices. Clearly, based on similar polarity and intermolecular forces of attraction, if we wanted to dissolve methanol and make a solution, we should choose water as our solvent to do that, because the hydrogen bonding intermolecular forces of attraction in methanol are similar to the hydrogen bonding intermolecular forces of attraction present in water. Therefore, a mixture, a solution between methanol molecules and water molecules will readily occur because they both are polar molecules. They can hydrogen bond with themselves and with each other and form a mixture, a solution.